左边的啊，然后我放一下 PPT，看看对吗？PPT 是用的，复制一下，应该怎么？正切换置放呀，应该是撤销，然后切换，对了，对了啊。Hello everyone, can you hear clearly?
你好，老
你
徐。
好，老徐。
你好，能听见吗？能听清吗？
你
能听
你
见。
啊，谢谢谢谢。呃，we have yeah, I saw 林雨峰right 可以听见，Sue side 可以听见，this course named heat and mass transfer and in Chinese. I think most of you your Chinese are very good. I can heard from what you said just now. And the name of this course, the Chinese name, 热质传递 heat 热质 mass 质 transfer 传递and 和热和质的传递。So we called this course name 热质传递 heat and mass transfer and and this is the teaching calendar. You can see from this table, this the first course, first class today. This the first class, and on Wednesday we have the second class. This the date for that, and the next several weeks, this the date for every class. And you can see here, this class I will talk, and 3 times after that, it's your turn to do oral presentations, and 3 times for my talk. And after that, your presentation time is this time. So we have totally 2 times for you to do oral presentations, and each time we have 9 students. Each time only 4 students to do that. 4 to 5 students to do the discussion, the oral presentations for this time. It's the teaching calendar. And what used for our examination, the oral presentations is your final presentation. So one oral presentations, around 15 minutes for each student for my class, and the topics related to heat and mass transfer, and best related to your master research topic. I'm not sure if all students are master students. Sometimes maybe 1 or 2 PhD students, but most of them are master students. So best relates to your master research topic. And finally, print the PPT files of the presentations and send the electronic versions to the WeChat group or the email address at the end of the course. This is what for examination. So look at this, the oral presentation time, this 2 times. Please do oral presentation carefully. And after each time you do the presentation, Dr. Tang and we will try to tell you how to revise your presentations. And you can revise it. And you submit the presentations, the slides for your presentations at the end of the course. After Professor Qi Hong's turn, the first half of the lessons is from me, and after that there are several courses from Professor Qi Hong. So you submit the presentation slides at the end of the course. So I can see if you improved your presentations or not, and use the final version as your final exam. So can you understand that?
Yes,
This,
Professor.
yeah, can clearly, yeah, it's clear for the final exam. We don't have any other exam. We just to require you to do a one oral presentations and print the PPT files, the slides, and send the electronic versions to the WeChat group or to the email address of Dr. Tang at the end of the course. So if you are not clear, you can ask me after that. Yeah, Ho Sai Yin said, okay, clear for that. Thank you. So the first of all, you introduce yourself and I would introduce myself. And this me, a professor from Harbin Institute of Technology, School of Energy Science and Engineering. And my name is Yurong He, and in Chinese is He Yurong. And the research areas for me about these three aspects. The first one about multiphase flow and heat transfer. And the second one, energy storage process and enhancement. And the third one, solar energy utilization for new energy or renewable energy utilization. This is what I research for. And I saw the 4 of you from the same school, of me from School of Energy Science and Engineering, and 5 other students from mechanical engineering, but we all from the mechanical field. So our research topic are similar and we can help each other, not only in the class, but also after class when you do your research topic, we can help each other, your students, and me and Dr. Tang, we can talk some research problem after that. And this is what about me. And this is the homepage. You can see here. This is, you can see from the Harbin Institute homepage address here, this one. And my email address is rong@hit.edu.cn. And this is the homepage and the WeChat. You can see the WeChat group. You can see my WeChat ID there. This is my homepage. And Dr. Tang, can you introduce yourself first?
Okay, hello everyone. I'm the teaching assistant. I'm a PhD student of Professor Yu Rong, and I'm graduate. Teacher research is about multiphase flow in wet particle system, and I also have some investigate about heat and mass transfer behaviors in wet particle flow behaviors. So if you have any question and need any help about this course, you can contact me by WeChat and email. Thank you.
Yeah, thank you, Dr. Zhang. Every other student, can you introduce yourself? You can introduce your English name, your Chinese name, your country, your school, and your supervisor, your master research topic, your hobbies, your future plan, and so on. What you would like to talk here. Sue, can you be the first one?
Hello everyone, my name is Wu So-young and my Chinese name is Wu Su-yong and I'm from Korea. Now I'm in Korea and I graduated. My bachelor was HIT and my school is mechanical engineering and my
Who is your supervisor? Hello?
老师，我断了。
Hey. Do you know your
Yeah,
supervisor?
Yeah, 我的My supervisor is 赵立东老师。
赵立东。Yeah, I see.
And my
yes.
master topic is kind of 智能化管理。
智能化管理。
And my hobby is workout and exercise. And my future plan is I'm not yet think about.
Not sure. Yeah, not sure about that. Your future plan, for example, you would like to continue to do a PhD, or you will find a good job after your master.
If I graduate master, if I can, I want to continue study.
Oh, yeah, you would like to look for a PhD position.
If I can.
Yeah. Yeah, I think you can. I'm sure about that.
Yeah.
And I would like to know, now you are in China or in Korea?
Now I'm in Korea. 我大三之后回国了。
什么时候可以入学，可以来呢？When will you come?
这个我也不知道，因为学校不让返校，所以我的东西都还在哈尔滨。
I see. 你学了1年的汉语，然后学了1年汉语之后，进入课题的时候就一直还不能回来。
快3年。
快半年。I see. Yeah, I get that. Yeah, maybe you can contact with the International Student Center to see when you can get back.
Yeah, I hope so.
Yeah, I see. Thank you. And Suyong, can you be the monitor for this non-people? And if I have something to find the students, I will look for you, or maybe you can collect the slides for me from the students. It's okay?
Yeah.
Okay, thank you.
Thank you.
Thank you. Other students, can you introduce yourself?
Yes, Professor.
Yeah, hello, 纳瓦兹. How to pronounce your English name? Nawaz?
My English name is Shah Nawaz.
Shah Nawaz? Yeah, very good. And
my Chinese name is Nawaz.
Nawaz. Yeah, I see that.
And I'm from Pakistan.
Pakistan.
And my school is energy of science and engineering. School of Energy Science and Engineering.
Yeah, I see.
My supervisor name is Bashir, Guaino Liu Bashiro.
Liu, I can't. I'm not sure who's your supervisor.
My supervisor name is Bashir.
She.
Guaino.
Can you pronounce in Chinese?
I will write it down in a message.
She. It's
Can you see it?
logo. Logo. Yeah. I see that.
He's my
Your
supervisor.
supervisor's Chinese name is Le Gu. I see. Yeah.
But he told me that his name is Bashir.
Yeah. And
Actually,
what's the master research topic?
And I want to work on induction heating process.
Induction. 导热。
And my hobbies is I play cricket and other cricket sports.
Yes, sports. And do you would like you would like to continue to do a PhD, or you would like to find a good job after the master?
After to apply for PhD, I want to continue my
PhD.
study. Yes,
You would like to, yeah, that's a good idea. And any other to say to tell to us? And where are you now? In the campus or in your country?
I am in Pakistan, Kohat city, Kohat.
Oh, I see. Yeah. See. Thank you.
That's all.
Thank you, Namazi. Thank you.
Thank you, ma'am.
And yeah, the next student.
Yes, Professor.
Professor.
Yeah.
My name
Abdul Wahid.
I belong
from Pakistan. My Chinese name is Abdul.
Your Chinese name is. Can you write down your
Abdul.
Chinese name?
Abdul.
Yeah, I know Abdul. But I don't know how to write down that.
Abdul.
Do you know how to? Yeah. Do you know how to write your Chinese name?
Yes, Professor.
I can.
Yeah. Can you
I
send a
write,
message?
in Chinese?
In Chinese,
I
read.
I do not install.
I do not install
Chinese
keyboard,
but
I see.
I can.
Pinyin.
I can.
Yes, I can read
I
on
can
the white
read
paper.
on the white paper.
Oh, okay.
Right
Okay.
Write on the white paper.
Maybe later. You can write in the WeChat group. It's okay.
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 Okay. And
my,
continue.
my
school
of energy sciences,
of energy sciences
and engineering,
and
my major is
and
power
my major is
engineering
power
and
engineering and engineering thermophysics.
and my
And my supervisor, Honorable
Hong Kui.
Hong.
Hong Kui.
Who is Hong?
My supervisor.
My supervisor,
Hong Kui.
It's Qi Hong.
Hong Kui.
What's the surname?
Hong
Hong
Kui.
Hong. Dr. Chang, can you get that? Who's
I don't know.
I read
yeah?
I read the
I read the blog.
Lao Shi Hong
Long Shi
Wei.
Hong Wei.
祁红老师。
祁红, yeah, it's 祁红. Surname is 祁.
Chi. Hong Chi.
Yeah,
Hong
yes,
Chi.
祁红. Yeah, I
Chi.
get that. It's a Hong Qi. Yeah, 祁红 or Hong Qi.
Yeah.
The surname is Qi. Yeah, I get that.
Qi.
Yeah, thank you. Yeah,
Yes.
thank you.
Yes.
Yes.
And
Yes.
what's your master research topic?
New
New energy utilization.
Oh, that's
spe-
good.
Especially microalgae, microalgae simulation of microalgae.
It's macro scale
Algae.
or macro. Yeah, okay.
Biomass,
Basically.
and my hobby
And my hobby is playing cricket.
Playing guitar?
cricket
Sports match.
Sports, circuit.
my hobby
My hobbies.
my future
My
plan
future plan
to develop my
career as a researcher.
Your future plan to do what?
my future
plan to develop
my career
as a researcher.
Sorry, I can't get that. You mean to find
I
a
mean,
work or to continue to
continue to
study.
My research, study and focus on my research.
Oh, okay. Okay, thank you.
Okay.
Yeah, thank
Okay,
you.
thank you.
And yeah, I know your supervisor will teach this course also after me.
Oh,
And you will meet him here
yeah.
online.
I hope.
Yeah, you will. And you are in your country or in China now?
I am
I
in
am in
Pakistan,
Lahore, Pakistan.
Oh, I see. The same in your country.
Yes.
Yes.
Yeah, thank you. Thank you.
Okay,
It's
thank you.
Abdul.
Thank you.
Abdul.
Abdul.
My
Abdul.
pronunciation is
Abdul.
correct. Abdul.
Abdul.
Abdul. Yeah, thank you. The next student.
I will go.
Hello, Hossein.
Hello, Professor.
Yeah, hello, Hossein. Yeah, hello.
So my name is Mir Akib Hussain. In
Yeah.
Chinese, it's Hossein,
Yes.
and I am from India. To be specific,
India.
it's Kashmir. And my school, I completed my BE in India, and right now I'm in mechanical masters.
Yes.
And my supervisor is Chang Xinpin.
Zhang Xiangbin.
Yeah, I guess this is the right pronunciation.
Okay. And what's your
And,
master research topic about?
My research topic is about rehabilitation robotics.
Robot?
Yes, robotics, robots.
Yeah, robot.
Yeah, health related robots.
Okay.
Biomedical.
And about my hobbies, so there are like photography and cycling
photography. Yeah.
and workout.
A lot of
Yes.
hobbies. And what's your future plan?
So I'm more interested in academics. So maybe I may go into PhD after my masters.
PhD.
Yes.
Okay. Yeah. Okay. Thank you. And you are staying at home right now?
Yeah, I'm staying at home in India.
Oh, okay. Thank you. Yeah.
Thank you.
Thank you. Yeah, the next student.
Darwin.
Darwin. Yeah, Darwin.
Yeah, my name is Darwin Jimenez. I'm
do-
from Ecuador. My Chinese name is Daivin.
Chinese name
Uh,
is similar pronunciation of this.
Yes. I'm from Power Engineering and Engineering Thermophysics School, and my supervisor is Professor Han Lei.
Who? Your supervisor's name is?
Han
Sorry.
Lei.
Han Lei. I see. Yeah. Your supervisor's name, Chinese name, Han Lei. Your pronunciation is very good.
Yes. My master research topic is the simulation of pellet turbines using finite volume particle methods.
It's about hydro turbine.
Yes, hydroturbine.
Yeah, okay.
Yeah, as a hobby, I like to make beer. And my future plan is to continue studying a PhD.
PhD, continue to study.
Yes.
Okay. You're staying at home right
Yes,
now?
I'm now in Ecuador, and the city is Quito.
Okay. Okay, thank you, Darwin. And the next one, next student. And the next one.
I'll introduce.
Yeah, hello. Hello, Martin.
Hello, my name is Martin. My Chinese name is Mading. I'm from the School of Mechatronics. My major is robotics. My research direction is, my research direction is advanced prosthesis. And my supervisor is Fu Yili.
傅一丽，傅老师。
Yeah.
Yes.
After completing my program, I intend to work because I did some practical experience, and maybe in further years go for a PhD.
Okay. Maybe PhD. Okay, thank you. Yeah, thank you, Martin.
Yeah.
And other students, to introduce yourself, we have 3 students left.
Hello.
Hello, Lin Yufeng. Hello.
Yes. My English name is Lim Yufeng, and I'm from Malaysia.
Okay.
And I study mechanical engineering.
Yeah.
And I study my bachelor in HIT as well. And my supervisor is Li Yuefeng 老师.
Li Yuefeng.
Yeah, and my research topic is about simulation on the heat and pressure field of fluid.
Oh, heat simulation. Okay.
And my future plan maybe find a job to gain some working experience first and before considering PhD.
Okay, to earn money first.
Yeah.
Yeah, you know, for your country, we know famous of sports, Li Zongwei.
Yes.
The badminton player is very famous and very popular in China.
Yes.
Yeah. Thank you, Lin Yufeng. Thank you for your introduction. Yeah, thank you. We have 8 students today. Maybe one student cannot online right now. And we have 1 student left. The only one student who is not introduced himself. So please. Yeah, please introduce yourself. I can look for the last one. Who is that? Abdul. Oh, I see. Abdul used twice here. Show 2 Abdul here. So we have 2 students are not here today. Some students said it's not easy to be online on time because of the time difference problem. So I will contact them after the class. Thank you for your introduction of yourself, and thank you to join in the class. It's very difficult to keep online, and maybe some students have the time difference. It's not easy to be online on time. Thank you. So we will continue for our course. The contents of this course is about heat and mass transfer. So first of all, we will introduce some basic concepts for today, and maybe the second class we will to introduce some basic concept, and after that we will look at some fundamentals of convection heat transfer, because heat transfer there are 3 modes: conduction, convection, and radiation. And just now I heard Namazi, the research topic about for him is about conduction heat transfer, 导热. We will study conduction, convection, and radiation heat transfer, and we will also learn something from this course about mass transfer. So we will study heat transfer and mass transfer in this course. So the first one, the chapter 1 is introduction and basic concepts. Chapter 1, 第一章 introduction and basic concepts, 绪论与基本概念. So the first chapter we will introduce some concepts. Maybe somebody, maybe Su Yong, maybe Lin Yufeng have learned something when you are undergraduate student. But some students may are not familiar with this. So we will first introduce the basic concepts. And what the objective of chapter 1? First, understood how thermodynamics and heat transfer are related to each other. You know, we have heat transfer and mass transfer. We have this course, and we also have a course named thermodynamics. So how to understand these 2 courses relate to each other, and these 2 named thermodynamics is one course from Haochun Zhang, and the other heat and mass transfer. Here they relate to each other. We will understand how they relate to each other, and we will distinguish thermal energy from other forms of energy. Thermal energy, and there are other forms of energy. We will distinguish thermal energy from other energies, and heat transfer from other forms of energy transfer. You know, the energy transfer, and we will distinguish the heat transfer from other forms of energy transfer, and perform general energy balances as well as surface energy balances. Energy balance is very important when we solve the problem related to heat or related to energy. So we will get energy balance. So perform general energy balances as well as surface energy balances is important to solve the problems. And understand the basic mechanisms of heat transfer, which are conduction, 导热 convection, 对流 and radiation, 辐射. And Fourier's law of heat conduction, Newton's law of cooling, and Stephen Boltzmann law of radiation. They are three laws are very important for heat transfer. For conduction, natural convection, and radiation, we have three important laws. And to identify the mechanisms of heat transfer that occur simultaneously in practice, we will find out mechanism. When we do our master research, you will identify the mechanism, not only for heat transfer, but for when you do some simulation on robot, maybe you have some mechanism to find out, not only to just see the phenomenon, but also to look for the theory in that. And develop awareness of the cost associated with heat losses. Heat losses is very important for when you make a heat balance, and solve various heat transfer problems encountered in practice. And what we learn, what we learn heat transfer, we would like to solve the problems encountered in practice, maybe in industries, in life, and in other areas. So we would like to solve the problems encountered in practice. This is the objectives of this chapter and is this course to do. So first of that, we would like to distinguish the thermodynamic and heat transfer. They have relationship with each other and they are different. And what is heat? Heat is the form of energy that can be transferred from one system to another as a result of temperature difference. So there is a very important word, temperature difference, 30. If we write down that, it's 30. So temperature difference is very important. Heat is the form of energy that can be transferred from one system to another as a result of temperature difference. So the reason for heat happens that because of temperature difference. And we look at this sentence. From one system to another, that means we will have system. There is a system and the heat and the energy will be transferred. The heat will be transferred from one system to another. And because of the temperature difference, that is the heat. And what is the thermodynamics? It is concerned with the amount of heat transfer as a system undergoes a process from one equilibrium state to another. You look at this sentence. This sentence is about a process, and there is a system. A system undergoes a process, and this process is from one equilibrium state to another. From one equilibrium state to another. That's a process. And what is this process is for a system. So that's the thermodynamics means concerned with a amount of heat transfer as a system undergoes a process from one equilibrium state to another. And what is heat transfer? Heat transfer deals with the determination of the rates of such energy transfers, as well as variation of temperature. Heat transfer will deal with the determination of the rates of such energy transfers, as well as variation of temperature. So there are temperature variations. That is heat transfer. The transfer of energy as heat is always from the higher temperature medium to the lower temperature one. What is about the heat transfer is always from higher temperature to the lower temperature. Heat transfer stops when the two mediums reach the same temperature. The high temperature equals to the lower temperature, so the heat transfer will stop. So the heat can be transferred in three modes. We know that is conduction, convection, and radiation. These are the examples. Look at the figure. The left one is a Thermos bottle. That is a very good brand for the bottle, the Thermos bottle. The hot coffee inside, you can see the hot coffee inside, and outside there is an insulation layer for this bottle. And we are normally interested in how long it takes for the hot coffee in a thermos bottle to cool to a certain temperature. Yeah, because it's too hot. It's not healthy. It's not good to drink very hot coffee. So we would like to know how long I can drink this hot coffee. So the hot coffee in the thermos bottle will be cooled to a certain temperature, which cannot be determined from a thermodynamic analysis alone. If you learn thermodynamic, you can set a balance, but you can solve this only by thermodynamics. We will use heat transfer knowledge to solve this problem, to know how long you can drink the warm coffee, not the hot coffee. And look at the red, this one. This hot coffee at the temperature of 70 degrees Celsius, and it's hot. We cannot drink this time. And outside is the cool environment. The cool environment at the temperature of 20 degrees Celsius. So the heat will transfer from the hot coffee inside to the environment. The heat flows in the direction of decreasing temperature. So the heat transfer happens here and here. But you know there is an insulation layer for the thermos bottle. That is why it's good to keep warm. So the heat is not easy to be transferred from inside to outside for this bottle. For this bottle, there is an open part. This is very easy to transfer heat from inside to outside to the environment. That's the examples for the coffee. Maybe right now you are drinking the hot coffee at home. But the heat transfer is not only in life, but also in many industries. Look at the applications of heat transfer in different areas. Look at the figure. This first one is for human body. People feel comfortable at some environment, some special temperature like this, and how watch the color of your clothes and how thick, what material. That is related to the heat transfer. So the human body, you feel comfortable and how to make your clothes. And this is very important. It's related to heat transfer. And this one is the air conditioning system. When you design the air conditioning system for industries and for people, you use this and you will make people feel comfortable. You will cool down the electronics. Like this air conditioning system is related to heat transfer. And you will use some heating systems. This you will also relate to heat transfer. You will use this knowledge to design the heating systems. And for electronic equipment, you know the chip. The chip is very important research topic to cool down the electronic equipment. So this one is a very popular research topic. And if you are studying on it, it's very easy to find a good job. And this is the power plants. For the power plants, it's related to heat transfer also. You will make an energy balance to calculate, to design the power plant or to revise it. And this is the refrigeration systems in your life. When you're at home, you will use that to find out a cold beer. Maybe this is cold beer inside. This is the application areas of heat transfer in your life and in industries. And what is the history? The history of the heat transfer. We will look at. In the early 19th century, heat was thought to be an invisible fluid. At that time, people are not very familiar with heat. What is heat? They don't know that. They think heat was an invisible fluid, like a fluid, like something is caloric that flowed from hot body to cold body. It's like this. The hot body is there, the pink one, and the green one is the cold body. When they touch each other, and the heat, like a caloric flow from the hot body to the cold body. This is the very old heat transfer knowledge. They think heat is a fluid-like substance that named as caloric, that is a massless, colorless, odorless, and tasteless substance that can be transferred from one body to another. That is heat transfer. And people treat molecules as tiny balls at that time. They think they are in motion and thus possesses kinetic energy. So the energy associated with the random motion of atoms and molecules is heat. So this is the history of the heat transfer. It was only in the middle of the 19th century that we had a true physical understanding of the nature of heat. That is from where James Joule. You know Joule? Joule is a very famous scientist. He published one famous paper in 1843. His publication convinced that heat was not a substance, and thus the history of the caloric theory of heat stops at that time. This is in the middle of the 19th century. It's 1843 in that year. So this Joule is very famous and he did a lot of work. He transferred a lot. So people use the energy unit Joule named after him. That is a famous British physicist. And maybe in future, one of you may be similar like Joule to be a great scientist, a great physicist, a great mechanist, and a great scientist to solve the mechanical problem or to solve the energy problem, and something named after your names may be similar as Joule. That is James Joule. And look at the heat transfer in engineering. You know the heat transfer equipment, such as heat exchangers, boilers, condensers, radiators, heaters, furnaces, refrigerators, and solar collectors. Some students just know that maybe he will do the research on the new energy. So about solar collectors are designed primarily on the basis of heat transfer analysis. The heat transfer problems, when you will solve heat transfer related problems, usually encountered in practice can be considered in two groups. One problem related to rating problem. Others may be sizing problem. If you will solve a problem related to heat transfer, you will classify it to see if it is rating problem or sizing problem. And what is the rating problem? What is the sizing problem? The rating problems deal with the determination of the heat transfer rate for an existing system at a specified temperature difference. So what is the rating problem? An existing system is there. You have a existing system, and you know it's at a specified temperature difference. So determination of the heat transfer rate for this is the rating problem. What is the sizing problem? It deals with the determination of the size of a system in order to transfer heat at a specified rate for a specified temperature difference. You know, we don't have an existing system for the sizing problem. We would like to determine the size of the system. And in order to transfer heat at a specified rate for a specified temperature difference. So for rating problem, we have a system already. And for the sizing problem, we will determine the size of the system. This is the two kind of problem: heat transfer problem, rating problem, and sizing problem. An engineering device or process can be studied either experimentally or analytically. That means if you solve an engineering device or process, you can do experiment to solve the problem. You can do analysis, or you do calculation. You do numerical study, simulation to solve the problem. There are different methods to solve the problem. The experimental approach has the advantage that we deal with the actual physical system, and the desired quantity is determined by measurement within the limits of experimental error. You know, the experimental error is very important when you do experimental research. But I think because you are at home, experimental approach is not very proper for your situation. Simulation analysis may be proper for you right now. However, this approach is sometimes expensive, time-consuming, and often impractical for you right now, it's impractical because you don't have the setup of the measurements at home. And the other one is the analytical approach, including the numerical approach. This method has the advantage that it's fast and inexpensive, but the results obtained are subject to the accuracy of the assumptions, approximations, and idealizations made in the analysis. So if you have you make codes, if you use the commercial software to do your master research, maybe it's easy for right now. You are at home, you have a computer, you can do that. So the analytical approach is proper for your situation right now. And this approach has the advantage that it's fast. If your computer is good, it's fast and it's inexpensive. But the results, this result, people will thought your results can be believable, is accurate. So you will do some assumptions for the simulation. You will do some approximations for that. That is for analytical approach. So sometimes what is the good approach to do research? That's both experiment and numerical approach together, combine these two. But if you don't have your own experimental results, what can you do? You can use others' experimental results to compare with your analytical or numerical results to prove your analytical results. That is what you can do. We can have a rest first, a 5 minutes break, and after that we will continue. Hello everyone. Yeah, back to the course.
你好，老师。
Just now, 哎呀，你好，大家可以回来接着上课。Yeah, continue to the class. 啊，听不见。没共享吗？
现在就是共享的状态。刚才显示的是竖屏。
你现在看着呢？
现在还是竖屏。
我应该是切换，是不是？对吗？对吗？不对呀。不是你，是我的，我那个重新共享一遍就行。Sorry about that. I will show the presentation. 好了吗？好了。Yeah, sorry about that. And just now the screen shows different. So we continue for the lesson. Just now we introduced the heat transfer engineering problem classification. So this is how to do a modeling in engineering. Look at the figure. This figure is a very easy problem for heat transfer. This potato in the oven. You see here is a potato. This is the actual problem for engineering or for your life. But if we simulate this problem, solve the problem, we will do some assumption. this water, we think this potato is this water part, and the irregular shape is a circle face. This is the ideal model. So modeling is a powerful engineering tool that provides great insight and simplicity at the expense of some accuracy. You see the potato like this, and we assume this like a circle. And this is the actual potato, and we assume that is water, and with at some temperature. So look at a mathematical modeling for a physical problem. There is a physical problem, and first we identify the important variables for this. For example, the temperature is very important for this problem, and we make reasonable assumptions and approximations. For example, we think this is a round one. It's not like this irregular shape. This actual one is like this, but we make some assumption, and we think this is not potato, is some water. This water will be increase the temperature. That is this one, and we will apply relevant physical laws for this problem. We will apply for conduction heat transfer, radiation heat transfer, convection heat transfer. We will use different laws, the physical laws, to make an energy balance equation for this problem. So we get differential equations, and for this one we cannot just calculate that, use the whole shape. We will use different mesh. We will tell that after this. Just now we just know we will get differential equations for this problem, and we will apply applicable solution technique how to solve this differential equation. So we will apply some technique, and for this problem we will apply boundary and initial conditions. For this boundary, the oven, and for this potato, for the water and the boundary, heat transfer boundary conditions and other boundary conditions. And initially, if it's an unsteady problem, so the initial condition, initially the temperature is at 175 degrees Celsius. That's the initial conditions. And finally, we get the solution of the problem. That is how to solve a physical problem. It's like this. So before we solve one exact problem, we will know many concepts. First, the heat and other forms of energy. Energy can exist in numerous forms, such as thermal energy. Thermal energy is very common. And mechanical energy. Some students from mechanical engineering, so you know mechanical energy. And kinetic energy, potential energy, and electrical energy, magnetic energy, chemical energy, nuclear energy. Look at those energies. Nuclear energies, this relate to magnetic energy, electrical energy, relate to many popular research topics. You can use electrical field, magnetic field, and you can solve some nuclear engineering problem. So those energy types is very important when you solve some industry or your research topics problem. There are some constitutes the total energy E. The capital E is the total energy E is those energy together. And if the energy on a unit mass basis is like this, the sum of all macroscopic forms of energy is called the internal energy of a system. Internal energy. The internal energy may be viewed as the sum of the kinetic and potential energies of the molecule, and the sensible heat is the kinetic energy of the molecules. The latent heat is the internal energy associated with the phase of a system. The chemical energy is the internal energy associated with the atomic bonds in the molecule. The nuclear energy is the internal energy associated with the bonds within the nucleus of the atom itself. Those energy looks very simple, but when you solve the research problem, it's very important. For phase change problem, the latent energy is very important. For phase change problem, phase change is a energy storage form, very important, very popular research topic, energy storage. So the latent heat is very important for that. And for chemical energy storage, you use chemical energy, chemical bond energy. This is very important, and it's not very easy to learn for this chemical energy. It's related to atomic bonds. And for nuclear engineering is very popular in recent research field. So what is thermal energy? What is the difference between the thermal energy and the heat? We need to know more concepts about them. First, look at the internal energy and enthalpy. In the analysis of a system that involve fluid flow, we frequently encounter the combination of properties U and PV. Look at this figure. This is related to flowing fluid. So that encounter the combination of U, internal energy, and PV. U and PV together is the enthalpy. Is this the energy? Totally together is this. The combination is defined as enthalpy. Enthalpy is this, is the flowing fluid and internal energy and the flow work together. And the term PV represents the flow energy of the fluid. If the flowing fluid velocity equals to 0, then it is a stationary fluid. The energy just equal to the internal energy. There's no flow fluid, so there's no flow work. That flowing energy. We don't have flow energy here. That's for a stationary fluid. So the internal energy U represents the macroscopic energy of a non-flowing fluid. So the enthalpy H here represents the macroscopic energy of a flowing fluid for this one. And other concepts about this, specific heat of gases, liquids, and solids. We use specific heat. Usually, we use this to calculate heat transfer problem. The energy required to raise the temperature of a unit mass of a substance by 1 degree is specific heat. You can look at this one. Specific heat is the energy required to raise the temperature of a unit mass of a substance by 1 degree in a specified way. The mass for this system is 1 kilogram. The temperature is increase 1 temperature, so 1 degree Celsius. How many energy we need to increase the 1 kilogram this substance increase to 1 degree Celsius? We need 5 kilojoule. So the specific heat for this substance is 5 kilojoule per kilogram Kelvin. That is specific heat definition. Two kinds of specifics are, you know that from your postgraduate, maybe in your middle school or undergraduate study. You know the specific heat, CV and CP. What is CV? The specific heat at constant volume. And what is CP? It's specific heat at constant pressure. The specific heats of a substance in general depend on two independent properties, such as temperature and pressure. At low temperatures, all real gases approach ideal gas behavior, and therefore their specific heats depends on temperature only. At low temperatures, you know all real gases approach ideal gas, so the specific heat depends on temperature only. The specific heat of a substance changes with temperature. For example, if you would like to increase 1 kilogram air from 300 Kelvin to 301 Kelvin, you need 0.718 kilojoule. But if you would like to increase 1 kilogram air from 1000 Kelvin to 1001 Kelvin, you need 0.855 kilojoule. It's more difficult to increase the high temperature air to raise 1 Kelvin. So this is the difference. The specific heat of a substance changes with temperature. You look at the specific heat CV and CP. It seems very easy. The concept is easy. But when you do your research, you will know the change of CV and CP is very important for energy storage. If you would like to make some substance more capable to store energy, you should increase the CP or CV. That's an important concept when you do heat transfer or thermal storage problem. And some special situation is for incompressible substance. If a substance whose specific volume or density does not change with temperature or pressure, that substance is incompressible substance. For this one, the iron is incompressible substance. It's difficult to change the shape. The density won't change with temperature or pressure. That's the constant volume and the constant pressure specific heats are identical for these incompressible substances. So the specific heats of incompressible substance depend on temperature only. Just now we just introduced the CV and the CP, the specific heat. And I told you it looks very easy concept, but it's very important when you do the energy storage problem. The thermal storage problem is very popular and very important to store energy, especially for the students in School of Energy Science and Engineering. And if in the mechanical engineering school, you do some problem related to energy storage. So it's a very important variable, CV and CP. You remember that? And energy can be transferred to or from a given mass by two mechanisms, heat transfer and work. What is heat transfer rate? This is a heat transfer rate. And what is heat flux? And this is heat flux. Heat transfer rate is the amount of heat transferred per unit area. Per unit area, that means the total amount of heat divided by the time, divided by time difference. So you can get the heat transfer rate. And what is heat flux? Heat flux is the rate of heat transfer per unit area. So the heat transfer rate divided by the area, then you get the heat flux. And this is how you calculate the area. The area is the heat transfer direction, and it's normal to that. This is the area. And for thermodynamics, we have several laws for that. The basic one is the first law of thermodynamics. The first law of thermodynamics is the conversion of energy principle. It's important for heat transfer problem. The first law of thermodynamics, conversion of energy principle. The first law of thermodynamics states that energy can neither be created nor destroyed during a process. It can only change forms. Energy can neither be created nor destroyed during a process. It can only change forms. So this is the energy balance equation. Look at that. The total energy entering the system minus the total energy leaving the system equals to the change in the total energy of the system. So the net energy in the total energy of the system during a process is equal to the difference between the total energy entering and the total energy leaving the system during that process. This is the energy balance equation. The energy in minus energy out is the net energy transfer by heat, work, and mass equals to the ΔE system, the change in internal kinetic potential energies. The energy balance for any system undergoing any process in the rate form. This is the rate form of the energy balance equation divided by time. Divided by time is the rate. So the steady rate form for the first law of thermodynamics, you can see this. For the E input, E output, you can see that like this is 30 change in energies. But if for a steady system, there is no this part. For a steady state system, no change in the energy. So the rate of net energy transfer in equals to the rate of net energy transfer out. So the E in equals to E out. Look at the figure on the left. In a steady operation, the rate of energy transfer to a system is equal to the rate of energy transfer from the system. If you solve a problem related to heat transfer, then you have a system. If the system keeps steady, you can use this. The E input equals to E output. So what E input includes? includes the heat input, work input, and the mass input. And what the E out includes heat, work, mass output. So in heat transfer problems, it is convenient to write a heat balance equation and to treat the conversion of other energies into thermal energy of heat generation. If you think other problems, energies in the heat balance equations, you can think this other energy forms as the heat generation. Then you can write the thermal or heat balance equation like this. For different systems, for example, a closed system, then for a closed system has a fixed mass inside. So how to write the energy balance equation for this one? This is no work interactions because the fluid inside is stationary. The change in the energy content of a closed system is equal to the net heat transfer. So we will list the equation like this. For a stationary closed system, the energy in minus energy out, the energy input minus energy output equals to the delta U. And what is delta U? And is Cm delta T. You know Cm delta T is the mass, the specific heat, and the temperature difference. So it's easy for a fixed mass closed system. The total energy E for most system encountered.
Sorry to interrupt you, Professor. The screen is black.
Black. 黑屏了。
I cannot see anything.
Sorry, I will deal with that. 它怎么又黑屏了？结束共享。刚黑屏还是一直在黑屏？黑了2遍。那我再重讲一下。现在是新的共享是吗？现在能看到哈。
Now it's visible.
这个对吗？
It's okay, Professor.
对吗？Sorry. This page just now you can see this page.
Yes, we can see it.
You can see it. Yeah. I will repeat what I just now what I said here. For the first law of thermodynamics, that means how to write a heat balance equation. The heat balance equation is for a steady system. It's like this. The energy input equals to the energy output. The energy in equals to the energy out. In the steady operation, the rate of energy transfer to a system is equal to the rate of energy transfer from the system. So you can list this equation like this. Energy input equals to energy output. But for other energy forms, for example, the nuclear, chemical energy, mechanical energy, and the electrical energy into the thermal energy, like we can use like heat generation for that. For the equation, the heat generation for chemical energy, we think is a heat generation here. So we can list that term here for the energy equation, heat balance equation like that. And this one is a closed system. There has a top cover here. So in the absence of any work interactions, the fluid is stationary inside. So the change in the energy content of a closed system is equal to the net heat transfer. Like this, the energy inside minus energy outside equals to Cm/T. C is the specific heat, CV. M is the mass of the collar, and T is the temperature of the collar, and the specific heat is the collar's specific heat value for that. So you can list the energy balance equation like this. E input minus E output equals to C multiply CV multiply T, like that. This is for a stationary closed system. It's very easy to list the heat balance equation like this. And for the energy balance for a steady flow system, just now the system is stationary, the fluid is not flowing. But if the fluid is flowing through this tube, through this channel, what we can do? Many engineering devices such as water heaters and car radiators involve mass flow in and out of a system and are modeled as control volume. Control volume is an important word. You remember the control volume word. Most control volumes are analyzed under steady operating conditions. And the term steady means no change with time. Unsteady means change with time at a specified location. And look at this one. This the mass flow rate of a fluid at a cross section. This the cross section is equal to the product of the fluid density, average fluid velocity, and the cross section area. This is for the cross section. And for this one, under steady conditions, the net rate of energy transfer to a fluid in the control volume is equal to the rate of increase in the energy of the fluid stream flowing through the control volume. You can see this the inlet, this the outlet, this is the control volume. For this control volume, from the inlet, the energy in, this outlet, the energy out. So we can see the energy transfer for this is Cm/T, and M is this, the mass flow rate. It's like that. And what is mass flow rate? The amount of mass flowing through a cross section of a flow device per unit time. And if for volume, it's volume flow rate, it's the volume of fluid flowing through a pipe or duct per unit time. This is for the energy balance for a steady flow system. Usually, an important method we used is the surface energy balance, especially for heat conduction, radiation. Look at this. This is a wall. Assume this is the wall of your house, of your home, the wall here. This is the inside. This is the outside of your house. This warm inside, outside is very cold. And the wall is here. And the wall is very thick to keep the insulation material. So the heat will transfer from this part to this part because it's warm, this is cold, and through the wall, the conduction happens. And from this, there, the radiation, because the temperature is over than 0 Kelvin, then radiation heat transfer happens. So the radiation heat transfer here. And this part is because the air inside, cold air outside. So the convection heat transfer happens. And this one is the important one to see that this is the control surface. That is the control volume. This is the control surface, a surface. The surface energy balance is very important because a surface contains no volume or mass, so the surface contains no energy. Therefore, a surface can be viewed as a fake system whose energy content remains constant during a process. So the surface energy balance is very easy to be listed here. The energy input to the surface equals to energy output to the surface. Because the surface is just a surface, no energy, no volume, no mass. So it's very easy to list the energy balance equation for a surface. This relation is valid for both steady and unsteady stations, and the surface energy balance does not involve heat generation because the surface contains no mass, no volume, no energy. So there is no energy generation since the surface does not have a volume. So it's very easy to list that. So people use this a lot because the merits for the surface energy balance. So the energy interactions at your home, at home is your house. In your house, this is the wall. And how to calculate heat transfer problem? You can use this one, the surface of your house. Then the energy input equals to the energy output. It's very easy. It's related to heat conduction, radiation, and convection. It's very easy to list the energy balance. This is for the important method to list energy balance equations for a surface. So you remember for heat transfer problem, people are very likely to use this surface balance important one. So next class, we will introduce the heat transfer mechanism, include the conduction heat transfer, radiation heat transfer, and the convection heat transfer. So much for today, and thank you for your attention. Thank you.
Thank you, Professor.
Yeah, thank you. Thank you.
See, Professor.
See you next time. Yeah, see you on Wednesday. 谢谢你们，周三见，谢谢。
谢谢，再见。
谢谢，再见。